So we're going to finish chapter 7 with just a few more theorems. So theorem 741 looks at derivatives of transforms. Let's say we want to take the Laplace of t to some power times f of t. Well, that's going to require us to take a derivative of a Laplace transform of f of t. And how many derivatives we take really depends on that exponent. So if this is t to the first power, we're going to take the first derivative. If it's t squared, we're going to take a second derivative, and so on. So let's look at an example of applying this guy. So here, our exponent is a 1. So I'm going to say n is 1. Our f of t is the sine of kt, so we're being very generic here. So our f of s is the Laplace of the sine of kt. And we know that, going back to our formula sheet, would be k over s squared plus k squared. So we have all the pieces. Let's substitute everything in. So plugging into this formula, we're going to have negative 1 to the first. We are going to take that first derivative. So there's an understood one here. I'll write it in. Of this guy. So negative 1 to the first is a negative 1. I'm taking the derivative with respect to s of k over s squared plus k squared. So quotient rule would be bottom derivative of the top. Derivative of the top would be 0 minus top derivative of the bottom all over the bottom squared. So that's going to be 0. So we're going to end up with 2sk over s squared plus k squared quantity squared. So we would say the Laplace of this guy is equal to that. And likewise, if we wanted to go backwards and take the inverse Laplace of 2sk over s squared plus k squared quantity squared, we would get that guy back. Now, some of these are on the formula sheet, just to kind of show you where these are. This theorem is actually number 55 on our formula sheet. T to the n f of t. If we wanted to take the Laplace, we would get this guy. I'm not sure why that's fuzzy. There it goes. So we would get this. So that's our theorem 741. Now, some of the ones that are more commonly used are on here. So that t sine of kt is actually on this page, number 22. So you can see where it's coming from. It's just coming from theorem 741. Or using that line 55, which is that theorem. So now let's take this and let's solve an initial value problem. So like always, our first step is to take the Laplace. So if we take the Laplace of x double prime, we'll get s squared, capital XS, minus s x of 0, that's your initial condition, minus x prime of 0, And then take the Laplace of the 16x, 16x of s. And that's going to be equal to s over s squared plus 16. That's coming from taking the Laplace of cosine of 4t. So let's simplify this a little bit. If we were to plug those initial conditions in, x0 is 0, so that term's gone. This is just going to be a 1. So let's rewrite. So now we have that. So I'm going to do 2 steps in one here. I'm going to move that 1 over, but I'm also going to factor in excess out of that first and last term on the left. So now let's divide both sides by s squared plus 16. So we're isolating that x of s. So now we're at the point where we want to take the inverse Laplace. So that left-hand side is just going to be x of t. So if we look at our formulas, we want to match this up. And if we look at our sine formula, which is number 7, it almost matches. We're just missing our k here. So we could multiply that 4 in as long as we compensate with a 1/4 out here. So that becomes 1/4 sine of 4t. So now we have to look at this guy. And that's really coming from that last example we're using. It's also number 22. We've got the s squared plus k squared quantity squared in the denominator. We're just missing our 2k from the top. So in this case, our k is 4. So we need a 2 times 4 in the numerator. We can multiply it in as long as we compensate out here. So that would be a 1/8. And this guy would end up being t sine of 4t. So there's our solution to our differential equation. The next thing we need to talk about is convolutions. So, in general, it's not true that the integral of the product of our functions is the product of the integrals. So, we said we could, the Laplace of a sum is the sum of the Laplaces. But that's not necessarily true for multiplication. If we change this to a multiplication, that's not going to work. However, if there's a special product, and that special product is actually called a convolution, then this would hold. So the convolution theorem says that if we have two functions, f and g, they're piecewise continuous on 0 to infinity, and they're of exponential order. Remember, that guarantees us we have a Laplace of f and a Laplace of g if those conditions hold. Then the convolution, and we know it's a convolution because they're using the asterisks here instead of a multiplication. So the Laplace of f convoluted with g would be the product of the Laplaces. If two functions f and g are piecewise continuous on the interval from 0 to infinity, then their special product is written f asterisk g. So I would say that is f convoluted with g. And we can define it in terms of an integral. So we're going from 0 to t, and this is going to be f of tau, g of t minus tau, d tau. So we're integrating with respect to that Greek letter tau. And I believe it's spelled T-A-O. So a lot of this is just recognizing what we have. So let's say we want to take the Laplace of this integral. Well, if we were to let's go back to this definition here. The Laplace of that convolution, then by definition, that is going to be the Laplace of that integral here. We just have to identify what our f and g functions are. So if we look at this, do you see how this guy is matching up with that definition? We just have to figure out what f and g are. So we're taking the Laplace of, our f function is going to come from this. So that's going to be e to the t. And we're going to convolute that with our g function, which is going to be just simply the sine of t. So then, since this is a convolution, then we can take the product of the Laplaces of the functions. So e to the t is 1 over s minus 1. Sine of t is 1 over s squared plus 1. So there's our final answer. Taking this guy, which is actually a cleverly written convolution, and finding the Laplace of that. Now, if this were not a convolution, if it were just simply e to the t sine of t, that resorts, to solve that, we have to go back to that definition, unless there's a formula shortcut to it. So we would end up thinking about that this way. There is no shortcut for this. That is outside of a formula. Okay, so this is different than a product. It's a specially designed product, and it's called a convolution. And that convolution is defined to be that integral. So that's another definition. So likewise, if we were to go backwards, and we were to take the inverse Laplace of 2 multiplied together, these are Laplace transforms multiplied together, then that will define a convolution. So let's look at an example. Let's look at this guy. So we could actually think about this in terms of 1 over s squared plus k squared times 1 over s squared plus k squared. So we could think about this as our capital F of s multiplied by capital G of s. So then our f function for this example and our g function are going to end up being the same. So to find f of g, we really have to take the inverse of Laplace of 1 over s squared plus k squared. And that, using our formula sheet, looks like our sine, but we're missing the k here. We can compensate with a 1 over k out here. So then we're going to have 1 over k times the sine of kt. So there's our f of t, and that's also going to be your g of t. We would do the same thing, taking the inverse Laplace of that. So here's what we have. We want to take the inverse Laplace of f of s, g of s. We know that's defined to be a convolution. So we have our f of s, our f function, convoluted with the g function. And then we're going back to that definition here. So we're going to have to do some integration there. Oops. So that's going to be a 1 over k squared. I'm going to factor that guy out. Integrating from 0 to t. So this is going to be sine of k tau. Sine of k t minus tau d tau. So this is once again coming from that definition here. Our f function is sine of kt. Our g function is also sine of kt. But we are replacing that t with t minus tau. So you can see how that's working out over here. And then we had a 1 over k times 1 over k. So just factor that guy out. Now, we really need to simplify this guy, just to make this integration a little bit easier. So we're going to use that product to sum formula here. So for us, we are looking at sine of k tau, sine of kt minus k tau. I'm going to distribute there. So we're going to have 1/2 times. This is going to be cosine of k tau minus kt minus k tau. Minus cosine of our u plus v. And this is cosine of 2k tau minus kt minus cosine of 2k tau plus kt. I'm just kidding, be careful. These guys are going to cancel. This is just going to be a kt there. So watch your signs. Now, why would I not use some of those same formulas, sum and difference formulas that we talked about before? That's just not going to help us, I don't think, if we were to try to split that. Before, we ended up taking like a cosine of pi, which we got a nice number for, or a sine of pi, which we got 0 for. That I just don't think that's going to help us in this case, so that's why I'm going to leave it there. Keep in mind we're going to be integrating with respect to tau. So we're actually going to replace this whole piece with this guy. So we have 1 over k squared, integrating from 0 to t. This is going to be 1/2, so I'm going to pull that 1/2 out. Cosine of 2k tau minus kt minus cosine of kt. And we're integrating with respect to tau. So this is going to require a u substitution. We would need a 2k. We would compensate with a 1 over 2k. Integrating cosine, we're going to get sine. This guy we would treat as a constant, so we're just going to have that number times tau. And we're going from 0 to t. This is a definite integral. So a big one and a small one. We substitute in t for tau. We have 1 over 2k sine. This would be 2kt minus kt, which would be a kt, minus t cosine of kt, minus. Now we're substituting in 0. That's going in for that tau. So that would be 0 minus kt, which is just minus kt. Minus tau. And then we plug in 0 for tau here. We're going to get 0. So it's going to be minus 0. So I'm going to use some properties of sine. We know sine's an odd function, so we could pull that negative out here. Minus negative would make that guy positive. And then we can put those two terms together. So that's going to be a 1 over k sine of kt minus t cosine of kt. And then I'm just going to get a common denominator. Clean it up. So we're going to have sine of kt minus kt cosine of kt all over k. So there's our final answer. So as you can see, the inverse stuff, isn't as fun as some of the other stuff. But I do want to play with this idea of convolutions just a little bit more. So let's say we want to find the Laplace of t squared convoluted with te to the t. So because this is a convolution, the Laplace of the convolution ends up being the product of the Laplaces. So this guy, t squared, if we were to take the Laplace as 2 factorial over s cubed, this guy, remember, is an s translation. And we know that because of this e to the at there. So we could rewrite that as the Laplace of t, recognizing that s is going to go to s minus 1. So we have 2 over s cubed. The Laplace of t is 1 over s squared, recognizing s is going to s minus 1. So we're going to replace that s with an s minus 1. So it's going to be s minus 1 quantity squared there. So then final answer would be 2 over s cubed s minus 1 squared. So that would be the convolution, sorry, wrong thing. That's a convolution of those two. So let's do another one. Let's say we wanted to find the Laplace of e to the 2t convoluted with sine of t. So if we want to take the Laplace of that convolution, it's really just the Laplace of those two. We're going to multiply those Laplaces together. So then e to the 2t, if we were to find the Laplace, is 1 over s minus 2. Sine of t, if we were to find the Laplace, is 1 over s squared plus 1 squared, which is 1. So there's our final answer. So let's do another one. What if it's written this way in that integral notation? So it's really important for us to be able to recognize what that actually is. So what this is really just this guy, which is just a convolution. So that's really a function f convoluted with a function g, and then we're going to want to take the Laplace of that. We just got to figure out what f and g are. So let's think about it this way. We have a cosine of tau, so there's our f function, but we don't really have anything for g. However, remember, we could just throw in a 1 there and think about that as g. So our f is cosine of t. Our g is 1. There's an understood 1 there, so we're going to utilize that for our g. So the Laplace of that convolution is going to be the Laplace of cosine of t times the Laplace of 1. The Laplace of cosine of t is s over s squared plus 1. The Laplace of 1 is 1 over s. So our final answer is 1 over s squared plus 1. So you can just see how we're using that definition to help us get there. I don't want you to be scared of these because of that one problem that was a doozy. Let's do one more. Let's say we want to take the Laplace of this guy. So recognizing that this is the definition of a convolution. That's what's important here. That's what I want you to recognize. We've got to identify our f and our g functions. So let's use a trick here. Let's use that whole thing as f. So then g, once again, we could use a 1 to make this just a little easier. So we're going to have t sine of t. And then we're going to have a 1. Now, why would I want to do that? Because this guy does have a Laplace in our formula sheet. So, if we go back to our formula sheet, t sine of t, and we want to take the Laplace, that's number 22. And that Laplace is going to be 2s over s squared plus 1 squared, quantity squared. And then the Laplace of 1 is just 1 over s. So we're going to have some things reduce. So there's our final answer. What I really want you to get out of this is what a convolution is, what that definition looks like, and how to apply that definition for a convolution.